A very good morning to chairman, moderators, and all participants in the second ICAT 2022. My name is Wei Xian from Universiti Teknologi, Malaysia. As for today, I'm going to present about the viscosity of copper oxide nanofluid due to nanoparticles size and concentration. Without further ado, let's start with the introduction. Firstly, what is nanofluid? It is actually a two-phase system which contains nanometer-sized materials. And nanofluid basically consists of base fluid and nanoparticles. Base fluid is solvent like water, ethylene glycol, oil, or others. Whereas for nanoparticles, it could be metals, oxides, carbides, or even phase change material like soil. As we know, metals or metal oxides have much higher thermal conductivity when compared to organic materials and heat transfer fluids. So what past researchers did is they tried to grind the metals or even metal oxides into powder form, which is less than 100 nanometer, and then mix into heat transfer fluids. So in the end, they obtain a mixture which has high thermal conductivity when compared to their original form. And this is known as nanofluid. So let's talk a little bit about the history of coolant used. First, water was used as coolant in different cooling systems, but then it has low boiling point, 100 degrees Celsius, and unsatisfying freezing point. Then, ethylene glycol was introduced as an additive to be mixed into water, and this mixture has been widely used as conventional coolant in different cooling systems until today. As we can see, by adding different amount of ethylene glycol in water could increase the boiling point, and this is favorable to many industries as they require much higher working temperature. So nanofluid has been widely researched in different fields. For example, heat transfer, we have automobile, solar collector, or energy storage. Whereas for industry which requires high electrical conductivity is microelectronics field. And they found that nanoparticles could be a good substitute due to its high electrical conductivity compared to other materials. And based on literature, there are many factors affecting the thermophysical properties of nanofluid. And the four basic properties are thermal conductivity, viscosity, density, and specific heat capacity. And the most focused factors are nanoparticles and temperature. The less focused factors in past studies are degree of stability, nanoparticle size, and nanoparticle shape. As for today, our study actually focused on the effect of nanoparticle size on thermophysical properties of nanofluid. So we know that hydrothermal performance is rather important in industry. So there are many past researchers reported that they obtained low hydrothermal performance from using nanofluid. This is because the high pressure drop caused by the nanofluid. And why we have high pressure drop? This is due to the high viscosity of nanofluid. Okay, so what is hydrothermal performance? It is actually a ratio of heat transfer performance over pressure drop in a system. Of course, with high pressure drop, we will get lower ratio, and it means lower hydrothermal performance. And why nanofluid has high viscosity? This is due to high concentration of nanoparticles and small nanoparticle size. For high concentration of nanoparticles, we know that there are more nanoparticles in the system, and due to its solid particles, it will increase the overall viscosity of the fluid. But what about small nanoparticle size? So small nanoparticle size actually means more nanoparticles at the same concentration, whereby in a system, the number of collisions is increased. And due to the larger specific surface area from more nanoparticles, the local shear stress between the particles and the base fluid is increased, and this eventually increased the resistance of nanoparticles to flow through the fluid, and this caused high viscosity. So there are some interesting results from literature. So let's look at Jiafei's work in 2009. As the particle size decreases, viscosity of nanofluid will become more dependent on the concentration of nanoparticles. So in the study, they compared nanofluid with different sizes of nanoparticles, which is less than 20 nanometer and more than 20 nanometer. So with nanoparticles of less than 20 nanometers, they observed that the viscosity of nanofluid mainly depend on the concentration of nanoparticles. And then we look at the Nguyen's and Petrorizza's findings. They mentioned that at low particle concentration, nanoparticle size shows almost no effect on the viscosity of suspension, and the maximum concentration they reported is actually 0.006 volume percentage. And then regarding heat transfer performance, Wei Xian in 2007 found that coolant with larger nanoparticles has higher Nusselt number due to increased turbulent flow. So Nusselt number is actually an indicator for heat transfer performance. But on the other side, Haider in 2020, they found that larger particle size decreased the heat transfer performance. So from here we can see that there are no consensus between these two reports, and authors found that there are differences between the size of particles they use. So for Wei Xian, they were using 100 nanometer particles, whereas Haider they were using 135 nanometer of particles. And in the addition to that, they were not reporting on the stability of their nanofluids. Though this could be the instability of large size particles they used. So large size particles tend to agglomerate and sediment more easily compared to the smaller size particles. So the research gap we found in the literature is that from 2011 till today, there was only a research reported on the viscosity of copper oxide nanofluid due to different particle size. But then they considered only very low concentration, which is less than 0.02 volume percentage. So to fulfill the gap, this led to our research objectives. So we wanted to compare the viscosity of nanofluid with different particle size, but with more than 0.02 volume percentage, and then followed by the comparison of experimental data with some past correlations. So how did we prepare our nanofluid? So we used two-step method. Firstly, we mix water and ethylene glycol in 50-50% of volumetric percentage using a magnetic stirrer. And then we added copper oxide nanoparticles. So we had two different sizes, which is 10 nanometer and 40 nanometer, all in spherical shape, into the mixture of water and ethylene glycol, and then stir for extra 30 minutes using a magnetic stirrer. Lastly, followed by ultrasonication using the sonicator probe for 2 hours. For viscosity measurement, we were using real meter MCR92 under Anton Parr, and this device uses a concentric cylinder which requires a minimum of 60 ml of sample to obtain a reliable results. And we fix our shear rate at 100 per second and working temperature from 20 to 70 degrees Celsius. As for the stability of our nanofluid, we use sedimentation method, whereby we use naked eye to observe the sedimentation of nanoparticles in our sample without touching it for long duration. So for 2 weeks, all of our samples did not show any agglomeration or sedimentation, and this was good enough for us to perform the viscosity measurement because it lasted for like 1 week only. So for the first result, we were comparing the base fluid result with our nanofluid result. So we can see that viscosity of base fluid is much lower than the nanofluids. And when we look at the lowest concentration of nanoparticles, which is 0.025%, we can see that the 10 nanometer copper oxide increases the viscosity of base fluid by 7.8%. and 40 nanometer copper oxide increased the viscosity of base fluid by 6.2%. And in between these two particle size, it differs by only 1.6%, which is considered low. But when we increase the nanoparticles concentration up to 0.05, which is double, we can see that the difference between these two particle size is now more than 3%. Okay, so we look at the bar chart. So we compare the 10 and 40 nanometer copper oxide nanofluid at two concentration only, which is 0.025 and 0.05. So let's look at the orange and purple bar. So we can see that there are insignificant difference between the 10 and 40 nanometer at the same concentration. But then when we look at the red and blue bars, we can see that the 10 and 40 nanometers and 0.05% concentration has significant difference. So we can induce that particle size effect is not that significant at low concentration, which is in line with past studies. The next, we compared our experimental data with three different models, which is from ASME, Brinkmann, and Batchelor. So here we are presenting the 40 nanometer copper oxide nanofluids with different concentrations. So we can see that the experimental data fits perfectly with the Brinkmann's model when we are using 0.025 and 0.05 percentage of copper oxide. So when the concentration was increased from 0.1 up to 0.2, the gap between the experimental data and the Brinkmann's model is further away. So for this phenomenon, we will explain it after the next figure. So when we look at the 10 nanometer copper oxide nanofluid, we are not considering the ASME's model because its limitation to 20 nanometer of particles, and we were using 10 nanometer. So we only use our Brinkmann and Batchelor's models. So we can see that our experimental data fits perfectly with the Brinkmann's model at these two concentration. And for Batchelor's one, actually it slightly underestimated the experimental data, but it's quite close and the trend is similar as well. So why this happened? Because Brinkmann's model considers spherical shape, and we are exactly using the same shape spherical one in our experiment. And then for Batchelor's one, they consider Brownian motion. So we can say that both spherical shape and Brownian motion are important to predict the trend of the viscosity change due to temperature and viscosity. And this can be further proven by the 40 nanometer copper oxide nanofluids. So we can see that at low concentration, all experimental data fit into Brinkmann's model. But then when it comes to higher concentration, the Brinkmann's model stray further away, but then the Batchelor's model still keeping a close distance and the same trend as our experimental data at higher concentration. We can induce that both shape and Brownian motion factors are important in order to predict the experimental data more accurately. So as for conclusion, objective of this study had been achieved. At constant concentration, smaller size particles, which means increased number of nanoparticles, will exhibit higher viscosity than base fluid. At low concentration, the effect of different particle size on viscosity is minimal. This is the same as those past studies. And from our comparison with the models in past studies, it was found that Brownian motion is also responsible for the viscosity change. That's all from my presentation. Thank you.